Hi, this video will cover section 1.1 inverse functions. The objectives for this lesson will be to find inverse functions informally by exchanging x and y values, or maybe with a graph, and verify that two functions are inverse functions of each other. Also to use the graphs, like I mentioned, of functions to determine whether functions have inverse functions. And use the horizontal line test to determine whether functions are one-to-one. Now, the second objective, it says to determine whether functions have inverse functions. So it's important to mention that every function has an inverse, but that inverse may not be an inverse function. So we will do an example. And then lastly, we have find inverse functions algebraically. So we will also look at, of course, graphically and numerically. So here, to explain the basics of an inverse function, we're going to use the sets that we have here, set A and set B. And so set A is going to represent the domain of the function, and then set B will represent the range. And the equation that could be used to map those numbers, like 1 to 5, 2 to 6, 3 to 7, and then 4 to 8, will be f of x is equal to x plus 4. So if you try this, f of 1, if you substitute x with a 1, you will get 1 plus 4. So that is equal to 5. Okay. To 5. So that will give us the point 1 comma 5. And then if we substitute x equals 2, we will get 2 plus 4 by following the equation that we see here and substituting the x. And that will give us the y value of 6, and so on. So that's how the 4 points were found. And in this case, it's also important to mention that this is a linear function and the domain is all real numbers. However, here they are specifying the set that they want us to use as the domain. So we're not really saying that all the other numbers are not included in the domain, but for this particular example, we're only using 1, 2, 3, and 4 as the x values. So in this case, if we were to remember, this is the domain, and this will be the range, the output. So if we were to interchange the first and the second number, so for this order pair, if we interchange by just switching y and x, you don't need to do anything to the sign, so they will keep their own sign, either positive or negative. For the next point, it will look like this, 6 comma 2. And then we will have 7 comma 3. And lastly, 8 comma 4. So what we could say about that is that that will be the inverse function of f. And if you notice, we use the symbol here, f, and then it has that, it looks like an exponent, but it's read as f inverse. So f inverse of x. And that is a way to find the inverse of a function numerically, and by interchanging the first and the second coordinates of each of those order pairs. So the same order pairs that we have here are written down here. And the equation that will come from it, or the equation that will be used to find those points, if we didn't have the points already, will be x minus 4. And if you think about it, the function here, the original f of x had x plus 4. So if you think about what is the inverse operation of plus 4 or adding 4, it will be subtracting 4. And I mean, that's like a shortcut to find the inverse, but it does not always work because we could have a more complex equation. So don't just take the shortcut. We will be listing the steps to find the inverse function algebraically in the following slides. So what's going on here is that what happened, we had initially said that the domain of function f was the set of numbers, I believe it was 1, 2, 3, and 4, right? So then we map those numbers to function f, or to the range, by using function f. And so here, 1 was mapped to 5, then number 2 was mapped to 6, number 3 was mapped to 7, and number 4 was mapped to 8. So then we called that set of numbers the range of f. So what's going to happen now is that the domain of f is going to become the range of f inverse. And whatever was the range of f, now it's going to become the domain of f inverse. So they will be interchanged. So again, whatever was the range for f, now is the domain for f inverse. And whatever was the domain for f, now it's going to be the range of f inverse. And so the function will go in this direction. 5 gets mapped to 1, then 6 gets mapped to 2, 7 gets mapped to 3, and remember the equation is x minus 4, so yeah, 7 minus 4 will be 3, and then 8 minus 4 will be 4. So one interesting thing about inverse functions, so now at this point we know both equations, and we're going to use a skill that we learned on the previous section, which is composition of functions. And so what we're going to try to do is to compose, and first we're going to find f of g of x, and so that function is going to be, remember the one that comes second is the innermost function. And I'm sorry, I'm using g. I shouldn't be using g. I should be using f inverse. And we could do that because that's the name of the function. So just like if we had f of g, that's how we the notation we were using in the previous section. So f of g of x, and we call that function the inner function. So it is the one that gets substituted into the other. So just like we could do that with f and g, we could also do that with f and f inverse. So now in this case, f inverse is the innermost, the inner function right here. And remember the equation for f inverse is x minus 4. So that is what is substituted here. So for the function x plus 4, which is function f, we only have one x. So that is what we're going to replace with the expression x minus 4. So instead of x, we enter x minus 4, or we write that. And then we still have to remember about the plus 4 that we see here. So now we could clear the parentheses, x minus 4 plus 4. And of course, you know that we will get x plus 0, which is just going to be x. Okay, so now we're going to do the same thing, but in reverse. So f inverse of f of x, which is the same as if we were trying to find f inverse of f of x. So remember the function that is second, that's the one that goes inside the other. So it will be f inverse of f of x. Okay, so the equation, and I'm gonna just erase some stuff here. The equation that we have for f of x is here, x plus 4. So we're replacing that one, the notation, the function notation f of x, we're replacing that with x plus 4. So that tells me that x plus 4 is what we're going to substitute into the other equation or function, the inverse of f, in place of the x. So instead of this x here, we will replace that with x plus 4. So x plus 4. And then let's not forget that we have a negative 4. So if we clear our parentheses, we have x plus 4 minus 4, and that will give us x plus 0, which is also equal to 0. So that is no coincidence. Every time you compose two inverse functions, you are supposed to get x at the end. And x, I want you to think of the equation y equals x as the parent function of linear functions, but also we call it the identity function. And we call it that because the input is the same as the output. And remember how we came across the set of points for the f inverse numerically? Just by interchanging the x and the y values. That's how we found them. So yeah, that is why if you compose two functions, the idea is that one will undo the other, but we're not going to end up with a 0. We're going to get an identity function. So for example 1, we are going to find the inverse function, and we're still, I don't want to give you the steps, we're going to do it informally. So if you think about 4 is multiplying the x, so the inverse operation of multiplying by 4 will be to divide by 4. So f inverse will be of x, it will be x divided by 4, or we could also use the equation 1/4 times x. They have the exact same meaning. So now what we need to do is verify that our guess was correct by finding f of f inverse of x. So remember that means f of f, oops, I'm just repeating myself, f of f inverse. Okay, so we're gonna replace f inverse with the actual function for that, with the equation, which is 1/4 times x. So we're gonna look for f of 1/4 times x. And now what I'm gonna do is substitute that into function f. So here, in place of the x, we're going to change that with 1/4 x. So we can't forget about the 4. and then 1/4 x. Now, if we multiply the two fractions horizontally, we will get 4/4x, and we know that 4/4 is equal to 1. We have 1x, which is just x. So we're done verifying, not actually done, but done with the first half of the verifying process. The next will be to do okay, so I'm going to use the next slide for the next one. And what we're going to do on the next one is verify that I believe we did f of f inverse. Yeah, we did. So we did this one. And now we're going to do the other one. So f inverse of f of x. In other words, f inverse of f of x. Okay, so the equation for f of x happens to be 4x. So we're finding f inverse of 4x. And the equation for f inverse is equal to 1/4 times x. So what does that mean? That here the x is going to be replaced by 4x. So we will have 1/4, this 1/4, and then times 4x. So multiply horizontally, that's how you multiply fractions, and you will get 4x divided by 4. And remember that 4 divided by 4 is a 1, so we have 1x. And if the coefficient is a 1, we don't really need to write it, so we get x again. So what that means is that after you check composition in both directions, if you obtain the identity function, that's how we call the y equals x function, and then that means that we were correct. Our inverse was 1/4 x for in our original function given was 4x. Okay, so here we are in the table. They're generalizing what we just practiced and what I told you. And so if we do composition of the two functions, and we first could refer to them as f and g, but then here they become f and f inverse. So it is the same thing, function composition, and here we have f inverse of f. And so if you do get x for both, that means that those two functions that you had from the beginning, f and g, or if they are already given to you as f and f inverse, then they are inverse functions. Okay, and the domain of f must be equal to the range of f inverse, and the range of f must be equal to the domain of f inverse. So remember, we interchange the x and y values, or you could think of in terms of reversing the mapping like we did at the beginning of the video. Okay, so now graphically, since we already verified that for two inverse functions, after doing composition, you get the identity function, which is the equation y equals x. And the graph of that is the dashed line that you see here, and which is the parent function of the linear functions. It goes like this. And in this case, we have a dash because we're not considering it part of the function. But just to show you quickly, if the function f was the graph that I'm highlighting, then the inverse of that function will be a reflection across the line y equals x. Not across the x-axis, not across the y-axis, not across the origin, but across the line y equals x, which is the identity function. So remember how we started the section by interchanging x and y values. So in this case, for a comma b, we have the point after interchanging x and y, we come across the point b comma a. So that point will belong to the f inverse of x function, which is the inverse of f of x. And so that will be, if we were to interchange all of the points and graph them, we will come up with that graph, and they are reflected across the y equals x line, which is also known as the identity function. For example 3, we're going to verify inverse functions graphically. So we have one equation given to us, which is f of x is equal to 2x minus 3. And the other equation is f inverse of x is equal to 1/2 of x plus 3. So what we will have to do is graph them. And you could already see that the graphs are here. So you could graph this on your calculator or Desmos if you want to. And let's look at both of them. So for example, f of x is equal to 2x minus 3. So if we were graphing this on WebAssign or on paper, the first thing to notice is that we have a y-intercept here at -3. So y-intercept is the point 0, -3. So that point could be found here, 0, -3. And then we could see how the slope is equal to 2. So 2 over 1 will be 2 units up, 1 unit to the right from the y-intercept. So if we do that, it will be 1 actually, oh, I believe this is this will be a -2. No. Yes, it is a -2. So then it will be right here. That will be -1. So it will be 2 units up. So it's going to be from the y-intercept 1, 2, and then 1 to the right. So we get to that point right there, which is -1, 1. So it's just, I didn't notice the scale of the, if you notice, it goes by 2s. Like this is 2, this is 4, and then we have 6. Okay, so that line, and you know, we only need 2 points. I mean, you can plot more to be more specific. If you have your calculator, or if you're using Desmos, you could also look at the table and get coordinates for your points. Then the inverse function, which is f inverse of x equals, and it's the equation here. So I'm going to go ahead and distribute the 1/2. So 1/2 times x will be 1/2 x. And then 1/2 times 3, and that will be 3/2. Okay, so from here we have that the y-intercept is going to come from here. So it's the point 0, 3/2. Remember that x is always 0 for a y-intercept. And the slope here is going to be 1/2, which in terms of rise over run, it means 1 unit up. 2 units to the right. So first, let's go ahead and find the y-intercept, which is 0, 1.5, and that will be here. And then the idea of us moving 1 unit up and 2 to the right. So from the y-intercept, we go 1 unit up and then 2 units to the right, and we get that point. Here's the graph. And as you can see, they are both reflections of each other across the line y equals x. So in the next one, for example 3, actually this is for us to graph it, so let's just graph it. I'm going to pause the video and plot the points by using the points that are given here to me, and for function f. So I'm going to plot those points, and then for the other one, f inverse, it will be the points here. So I just plotted the points for f of x, and then for it's a lot easier because the scale of my Cartesian plane here is 1 for every square, 1 unit. So let's go ahead and just plot f inverse. So we have -1, I'm sorry, -5, -1, negative, oh, that is not, -5, -1 here. And then we have -3, 0. We have -1, 1, 1, 2, and 3, 3. So I can go ahead and connect the points, and you can see that they do have a point in common, and that is the point 3, 3, because if we reverse the order of the x and y, we would still get 3, 3. So that's where they intersect, and you could see that they are reflections of the line y equals x. So now moving on to the next concept, which is the horizontal line test. And in the previous sections, we worked with the vertical line test to test if a function was a function. I'm sorry, to test if the graph of an equation was the graph of a function. And so we drew a vertical line, and if that touch more than 2 points, then we said that's not a function. Okay, so we have another test, which is the horizontal line test. And for that test, like the name says, we will draw a horizontal line. Now, if that line touches more than 1 point, then we say that the graph is not, well, first of all, it fails the horizontal line test. So it's not a 1 to 1 function. So I'm actually going to erase this one here. Not a 1-to-1 function. And remember, the other one was the vertical line test. Let's draw something different. Okay, so we have our formal definition here, and it says that if a function f has an inverse function, if and only if no horizontal line intersects the graph of f at more than one point. So that is saying that if we intersect the graph at more than one point, then the graph that we're testing is not a one-to-one function, therefore is not going to have an inverse function. So if it is a one-to-one, if f is one-to-one, then f, actually I'm going to scroll down a little bit, then f inverse is a function as well. But the case that we have here, that is not a one-to-one function. So then if this was f, then f inverse is not a function. So the original function must be one-to-one for us to have an inverse that is a function. Now, you might recognize the function here is a quadratic function. And so we could have an inverse that will be a function if we restrict the domain. So for example, if we just take half of the function, then it will pass the horizontal line test. So we'll do an example. So let's see, this is another way to say it. If no horizontal line intersects the graph of f at more than one point, then no y value is matched with more than one x value. And so that is the concept of one-to-one functions, that even though for a function to be a function, the y value could repeat, if we want it to be a one-to-one function, then the y value cannot repeat. And so that's what we are saying here, that if we pass the horizontal line test, then it's because no y value is matched with more than one x value, meaning the y is repeating. It's, well, in this case, not repeating. That's what that statement is trying to say. And so that's what we call one-to-one functions, where the y is not repeating. So in this case, not only the domain corresponds exactly to one value from the range, but also the reverse is true. Only every element from the range is only matched to one element from the domain. So that's when we have functions that are one-to-one functions. And here we're using the words dependent and independent. Remember, we've been using x as an independent, y as a dependent. Okay, here we're going to do an example with the graph of x squared. And actually, we don't have the graph, so I'm going to draw that for you. Or actually, let's just go ahead and, well, let's go ahead and graph them on Desmos. Okay, so I am going to type y equals x squared, and you could see the graph here. It's in red. And so if I was to reflect every single point there, then the inverse function will be, I'm sorry, the equation of the inverse will be the square root of x, and also the negative square root of x. Oops. And I'm forgetting the negative sign. Okay, so there we have it. Now I'm gonna make this 2 disappear for a second so I can go over something. So if I was to trace a horizontal line, such as, let's say at 4, y equals 4, and press enter, then you could see here how the graph will touch 2 points. So that tells me that at negative 4 comma 4 and 2 comma 4, the y value is repeating. So then this is not a one-to-one function. So if I wanted to use it like that, to ignore the horizontal line test and then reflect every single point, I will come up with the following graph. And if we do a vertical line test on this graph, the one in blue, we will obviously not pass it because it will touch 2 points. So that means that the x value is repeating. So we have 4, negative 2, and we also have 4, positive 2. And that is because the horizontal line that we had here for the graph in red told us that that was not a one-to-one function. So then the inverse graph of that will not be a function. That's how it works. Now, when I say the only way that we can make it be a function is if we restrict the domain. So let's get rid of the horizontal and vertical lines. And as you could see, the only way that I could get the graph that you see here in blue is by graphing both the square root of x and the negative square root of x. So if I want to restrict the domain of x squared, y equals x squared, I could do something like this on Desmos. Let's see if I remember. So I could use the set, and maybe I don't need the comma. Maybe just the set notation. And I just want my x values to go, I want my x to be greater than or equal. Oh, and the set notation, it's here, this button here, that's what I use, the curly bracket. And then let's see, let's go here and say greater than, oh, but I don't want to get out of the curly bracket yet. So right there, and then greater than or equal to 0. Okay, it worked. So if you look at the equation here, that is how I'm restricting the domain. And so on the graph, you could see that Desmos is only graphing the right side of the parabola for x values that are greater than or equal to 0, so the right side. So that is what it means to restrict the domain. Now, if I do the horizontal line test on that part of the graph, it will pass because it's only touching the graph at 1 point. And so that means that if I take the inverse of that, it will only be the positive square root of x, which is there. And here, just to confirm, they are reflections of each other across the line y equals x. As you can see here, I'm going to just change the color of that one, and let's make it dash. There we go. Okay, so here's y equals x, and here is the inverse function, the positive square root of x right here, and then the function x squared with the restricted domain. Now, if I choose to restrict the domain for values that are less than or equal to 0, then the inverse function will not be that one. It will be the negative square root of x, which is right there. You can see they're also reflections of each other across the line y equals x. The same explanation that I gave you with the graphs could also be done with the tables. And so if you notice with the x squared, f of x equals x squared, we have the value of 1 repeating here and here, and we also have the values of 4 and 4 repeating. That's the one that we tested with our horizontal line. And so if we reverse those x and y numbers, remember this is y, so if we interchange the domain and the range, like how we have it here, then we will have 4 repeating here. We will also have 1 and 1 repeating. And so that is because we came from a not 1 to 1 function. We started there, and then we arrived to a not a function. So if you recall on my explanation, here we failed the horizontal line test. And with the other one, we failed the vertical line test. Because it wasn't a function. And what I did to make sure that they were the same is, not the same, I'm sorry, that f of x had an inverse function was to restrict the domain. And first we tried it with numbers that were greater, for x numbers that were greater or equal to 0. So we were looking at the right side. And if we do that, then the graph was the positive square root of x. And you can see there how the x value, it does not repeat. So here are the steps to find the inverse of the function algebraically. We have number 1, use the horizontal line test to decide whether f has an inverse. Because if it doesn't, then you might have to restrict the domain. Then second, you will replace f of x, if necessary, of course, with y. Remember, function notation, that's the output, so is y. Then you will interchange the roles of x and y, and then you will solve for y. After you have solved for y, then you will replace y with the notation for f inverse. And then to verify that you did it correctly, you could try to do function composition with f and f inverse. So let's do some examples. For example 6, we're going to find the inverse function algebraically by following the steps that were on the previous slide. So before we get started, we will do that on the next page. We have the steps listed here as well. We need to check if the graph of that given function will pass the horizontal line test. So I want to point out that the graph that we see here is not the correct graph for this function. So what we're going to do is graph f of x with the help of decimals. So I'm going to type y equals, and then the numerator, I'm going to enter it in parentheses. I forgot what it was. 5 minus 3x. So 5 minus 3x, and then close parentheses, and then divided by 2. So divided by 2. And that is, I'm just going to check. Yes, that is going to be the equation. And actually, if we write this like 5 divided by 2 minus 3x divided by 2, or we could say, and I mean, it will be the function. We could reverse the order. So we will have, this will be a linear function. Even though we have divided by 2, there's no x in the denominator. So the one that we have here, the graph, this is a rational function. We're going to study this type of functions when we get to 2.6. Anyways, we could also work this equation, and we'll do this after the other one. So you have one more example. So let's go back to this linear function that we have. And we're going to use that as our original function. So it is f of x is equal to, and we could actually just leave them like that. I think it was something like 5 minus 3x over 2. The one that was given to us. And the first thing will be to replace f of x with y. So this f of x, we're just going to replace it with the variable y. Then we have the same thing, 5 minus 3x over 2. Then we're going to do the next step, which is to interchange x and y. So the y is going to become x, and the x is going to become y, just like that. And then we're going to have to solve for y. So what we could do first is take this 2 that is dividing to the y. We could take that across and it will be multiplying. So we have 2x is equal to 5 minus 3y. I don't really need the parentheses anymore. Then the plus 5 is adding to the y. So if I take that constant across, it's going to be subtracting. So we will have 2x minus 5, and that is equal to negative 3y. So now the negative 3 is multiplying to the y because there's no sign in between them. And so because of that, we divide by negative 3, or we take the negative 3 across, so it will be dividing. So we will have 2x minus 5 divided by negative 3 is equal to y. This could also be written this way. Negative 2 over 3 times x, and then the 5 divided by the negative 3, it will give us positive 5/3 equals y. So the last step is to replace the y with the function notation, the inverse. So it will be that negative 2/3 of x plus 5/3. So Let's go ahead and check. So I'm going to enter here y equals negative 2/3. I'm going to enter that in parentheses. And then x, oh no. And then I believe the other one, oh, what was that? Plus 5/3. Plus parentheses 5/3. Okay, there we have it. And so let's just check. I should have kept my identity function here. Y equals x. And let's just make it dash. So that is the graph in green is the f of x, and the graph in purple is f inverse. So you could see they are both linear functions, and they are reflected across the line y equals x, as you could see there. Okay, so we're not going to check that they are inverses of each other. What I would like to do instead is show you how you can find the inverse of a rational function. So you have another example to use. So if we take 5 minus x and then 3x plus 2. Okay, so now for that equation, here is the correct graph. So if we trace a horizontal line, we know it will pass it. Therefore, the inverse will also be a function. So step number 1 is to replace f of x with y. Step number 2 is to interchange x and y. So the y and the x and the x. So we will have x is equal to 5 minus y over 3y plus 2. Now, here, because we have a fraction, it's not going to be as easy to solve for x. I'm sorry, for y, but not impossible. So we gotta solve for y. And what we're gonna do first is take the 3y plus 2 out of the denominator. So we know it's dividing down there. So if we take it across, it's going to multiply. And I'm gonna keep it in parentheses. Okay, now I am going to try to get the y out of the parentheses. So I'm going to have to distribute here x. So x times 3y is 3xy. And then x times 2, it's going to be plus 2x. Then on my right side, I have 5. And then I have a minus y. So I decided to write the terms that contain y in blue because I want you to notice how they are both not together, so we want them to be together. So I'm going to leave my 3xy there, and I'm going to take that negative y across, so it will be a positive y, where we'll go from subtracting to adding. Then on the right side, I will keep my 5 there, and the positive 2x will become negative 2x. Now, I feel like I did something wrong. Yeah, this plus 2 shouldn't be that. That should be plus y. Okay, remember it came from here. Minus y went to plus y. Okay, now what I want to do, since they both contain y, I am going to factor y out of there. So y, and if I take y out of 3xy or divide 3xy by y, I will get 3x. and y divided by y, or factor y out, it's plus 1. And then here I have 2x minus 2x. So then the last step here will be to take the 3x plus 1 that is multiplying to the y, we take it across all together, and it's going to be dividing on the right side. And so that's how you find the inverse of a rational function.